Welcome to today's paper reading. Today's paper is titled, Flying with Photons, Rendering Novel Views of Propagating Light. This paper was published on AR14 by Anagh, Malik and colleagues from the University of Toronto and Stanford University. The abstract introduces an innovative imaging and neural-rendering technique designed to synthesize videos of light propagation from novel, moving camera viewpoints. This technique leverages a new ultrafast imaging setup to capture a multi-viewpoint video dataset with picosecond-level temporal resolution. The dataset is combined with an efficient neural volume rendering framework based on the transient field, which maps 3D points and 2D directions to high-dimensional, discrete-time signals representing time-varying radiance. This approach naturally accounts for effects due to the finite speed of light, such as viewpoint-dependent appearance changes. The rendering process includes complex effects like scattering, specular reflection, refraction, and diffraction. Additionally, it demonstrates the removal of viewpoint-dependent propagation delays using a time-warping procedure, rendering of relativistic effects, and video synthesis of direct and global components of light transport. Ultrafast cameras operate at trillions of frames per second, capturing videos of light as it propagates. These recordings provide insights into the world at the speed of light, which is crucial for various applications. For instance, they help in understanding fundamental physical mechanisms, recovering material properties, and imaging through living tissue or behind occluders. The goal is to synthesize transient videos from arbitrary, dynamic camera viewpoints, enabling flexible visualization of light transport and opening new avenues for applications based on 3D representations of light propagation. Figure 1 illustrates the process of rendering transient videos of light propagation from novel viewpoints. The input consists of multi-viewpoint transient videos capturing scenes illuminated by diffused or collimated pulsed light sources. On the left, conventional images of the Kennedy and Coke bottle scenes are shown. In the center, grayscale transient frames rendered from novel viewpoints are composited over the color image of the scene. On the right, the entire transient video is visualized in a single frame using a peak time visualization adapted from Velton et al. 64. This visualization uses hue to indicate the time of peak intensity at each pixel and brightness to represent the magnitude of the peak intensity. The brightness is modulated over the time dimension to create color bands corresponding to equitime paths, isochrones, revealing the shape of propagating wave fronts. In the realm of time-resolved imaging, various techniques have been developed. Interferometry offers the highest temporal resolution, resolving light propagation at micron scales. Street cameras achieve sub-picosecond resolution but are bulky and expensive. SPADs, on the other hand, provide a balance with high temporal resolution at the picosecond level and are relatively inexpensive. Transient rendering focuses on modeling light transport effects due to the finite speed of light, accounting for propagation delays and various optical phenomena. Neural rendering techniques, such as NERFs, have been used for 3D reconstruction and novel view synthesis, particularly for complex light transport effects. Transient NRF is notable for synthesizing the direct component of transient measurements, but lacks the capability to render indirect light transport effects. The SPAD measurement model describes the interaction of light with a scene and its detection by a SPAD. The photon radiance along array is modeled as h, r, t, and the expected photon count lambda, n, is the integral of this radiance over time. The detections follow a Poisson process with a rate function lambda, n plus b. Transient fields use a volumetric representation to render the transient tau r given a camera array. This involves a neural mapping tau theta that outputs discrete time bin values and an absorption coefficient. The transient is computed using a modified volume rendering equation. The optimization procedure involves minimizing a loss function L, which sums over all viewpoints, camera arrays, and time bins. A gamma function is applied to compress the dynamic range of the transients. Training typically requires 500K to 1M iterations, depending on the dataset. In Figure 2, we illustrate the process of casting a ray into the scene and querying a neural representation at various samples along the ray to retrieve an n-dimensional transient tau theta and density value sigma for each sample. Each element tau theta, n, of the transient corresponds to a time bin of width w times the speed of light c. We then time shift each transient based on the time delay from the camera origin O to Rs and composite them together using volume rendering. The neural representation parameters are optimized to minimize the difference between the rendered transient tau r and the captured transient tau r. The multi-viewpoint transient dataset is generated through both simulation and hardware capture. The simulated dataset uses renderers from Liu et al. 34 and a modified Mitsuba 2 58 to create transient videos from multiple viewpoints. The illumination is a point source emitting a temporal impulse. The hardware prototype includes a single pixel SBAD, a 2D scanning galvanometer, and lenses, capturing transient videos at 512 by 512 resolution with a time resolution of approximately 70 ps. Calibration of the camera intrinsics and extrinsics is performed using MATLAB and CalMap, respectively. The captured dataset consists of 5 scenes, each with 45 or 75 transient videos captured on a grid of 15 or 25 by 3 viewpoints. Figure 3 illustrates the multi-viewpoint capture setup. The gantry system is responsible for controlling the elevation angle of the scanning SBAD, single photon avalanche diode. The scene and laser source are mounted on a rotation stage, ensuring they move together during the capture process. The SBAD is synchronized with a 532 nanometers laser that emits light pulses of approximately 35 picoseconds duration. This setup allows for precise and dynamic capture of transient events from various viewpoints. Table 1 evaluates the rendering of transient videos from novel viewpoints, reporting parameters and time for different methods. Key metrics include the number of parameters, 15m, 37m, 43m, render time, 7.1s, 320.7s, 37 minutes, and PSNR, 26.349 dB, 20.551 dB, 32.965 dB. The table highlights the efficiency and accuracy of each method in rendering transient videos. In the evaluation of the proposed method for transient rendering, we first conducted simulations on 4 different scenes: pots, peppers, Cornell box, and smoke. These scenes were rendered using a modified version of Mitsuba 2, with the exception of the smoke scene, which used a method by Liu et al. The results showed that the proposed method outperformed existing baselines in terms of both accuracy and computational efficiency. For captured data, we evaluated 5 different scenes, observing similar trends to the simulated data. Due to the finer temporal resolution required, the number of parameters in the K-planes model was increased, which improved performance but at the cost of longer inference times. Additionally, the proposed method was applied to various applications, including time warping for better visualization, relativistic rendering to simulate effects at relativistic speeds, and direct global separation for 3D visualization of light transport components. Figure 4 presents simulated results rendered from novel viewpoints for the peppers and smoke scenes. The first and fourth rows show the ground truth integrated transient alongside transient plots for all methods, demonstrating that the proposed method more accurately represents both the direct and global components of light. The second and fifth rows display one frame of the transient video for all methods, composited over the integrated image of the scene. The third and sixth rows provide a peak time visualization of the transient in a single frame, where hue encodes the time of peak intensity, brightness is modulated by the maximum intensity, and each band corresponds to an isochrone, or wavefront of equal path length. Figure 5 presents the captured results rendered from novel viewpoints for the David and mirror scenes. In rows 1 and 4, one frame of the transient video is shown for all methods, composited over the integrated image of the scene. Rows 2 and 5 provide peak time visualizations, while rows 3 and 6 display transient plots. Due to the sparse and quantized nature of the measurements, the captured photon count is represented using scatter plots instead of continuous lines. The methods employed reconstruct a continuous approximation of the underlying transient and effectively suppress the noise observed in the captured data. Figure 6 illustrates relativistic rendering and time warping techniques. On the left, It showcases relativistic effects such as Lorentz contraction and the searchlight effect when the camera moves towards and away from the scene at a fraction beta of the speed of light. On the right, it presents peak time visualizations of the Coke bottle scene with and without depth-based warping, demonstrating consistent transient appearance across different viewpoints. This figure highlights how depth-based warping enhances the intuitive visualization of light transport and dynamic scenes. Figure 7 illustrates the direct global separation technique applied to the David scene. This visualization method highlights the global illumination components, which include complex effects like interreflections on the wall and subsurface scattering within the candles. By separating these components, the visualization provides a clearer understanding of how light interacts with the scene, capturing both direct and indirect light transport. The authors introduce a method for flying with photons, which involves rendering propagating light from novel, moving camera viewpoints. This technique opens up potential applications in education, art, and scientific observations of ultrafast phenomena. The main focus is on rendering and visualizing transient phenomena, which provide rich scene information. However, the method is currently limited to static scenes due to long acquisition times. Future work aims to reduce these times and potentially capture transient effects within dynamic scenes, leveraging advances in multi-viewpoint transient videography. The authors would like to express their gratitude for the financial support received from various organizations. DBL and KNK acknowledge the support of NSERC under the RGPIN, RTI, and Alliance programs. Additionally, DBL acknowledges support from the Canada Foundation for Innovation and the Ontario Research Fund. RP acknowledges the support of the Stanford Graduate Fellowship Program. In this section, we will briefly review some of the key papers and techniques that have contributed to the field. Abramson's work on light in flight recording by holography is foundational. Ament et al. Introduced the refractive radiative transfer equation, which is crucial for understanding light transport. Adel et al. Developed TORF, a method for dynamic scene view synthesis using time-of-flight radiance fields. Bemina et al. Proposed Eikenhoff fields for refractive novel view synthesis, while Chow and Johnson introduced hexplane, a fast representation for dynamic scenes. Deng et al. Contributed with depth-supervised NERF, which allows for fewer views and faster training. Faccio, Velton, and Wetzstein explored non-line-of-sight imaging, while Gao et al. Achieved single-shot compressed ultrafast photography at high frame rates. Gary P. et al. Demonstrated single-photon-sensitive light-in-flight imaging, pushing the boundaries of what is possible with photon detection. The proposed method builds on the instant NGP implementation of NERF ACC, using an occupancy grid with a threshold of 10 to the power of -2 for binarization. Data preprocessing involves dividing by factors given in table S1 and S2, followed by tone mapping with gamma correction, where gamma is set to 5 for simulated data and 2 for captured data. Transient NRF is implemented using the NERF ACC framework without any preprocessing applied. Thank you for watching.